Hi everybody. Today we're going to talk about a particular force that, well, in physics we like to ignore for as long as possible, but now we can't. Something called friction. Now a lot of people know what this term is. For example, if you rub your hands together really hard, you can kind of feel something that's really happening. But what really makes up the idea of friction? Well, to begin with this idea of friction, let's look at an example. So here we've got a 50-kilogram crate, and we got a little guy who's going to start pushing on it. Okay, so let's have him apply a force of, say, 20 newtons. Now, notice that the box isn't going anywhere. Okay, and although we don't see anybody on the right side here pushing against him, there is a force pushing against him, some sort of frictional force. Now, it's kind of hard to see here, but it's saying right now that the frictional force is also 20 newtons. So it kind of makes sense that it's not moving, because if he's pushing with 20 and this mysterious other force is pushing back at 20, the system's in equilibrium and therefore can't go anywhere. So let's increase his pushing force to, say, 100. Whoa, wait, it's still not moving. And notice that the amount of friction force has now also gone up. Well, that's kind of strange, because even though he's pushing harder, friction was able to sort of seems to change itself and is now also pushing back even harder. Well, let's try another number. Let's try 124. Still didn't work. Still can't seem to get this going. So he's pushing harder and harder and harder, and yet this box seems to be resisting this intended motion. He's trying to move the box, he intends to move the box, but it's resisting that intended motion. Nope, that didn't work. Still kind of even there. Ooh, wait a minute now. Suddenly, he has an applied force of 126 newtons, and yet friction stayed at 125 newtons, and look, it's slowly starting to move. Well, that means this friction number must have maxed out at a certain value. Notice it kept staying the same and same, and now it seems to have hit a very specific value. So something must occur that there's only one sort of limited value in here. But now as he moves forward, even though he's applying 126 newtons, and it's actually moving, friction's still resisting, still pushing back on him. But the box is now moving because now there is a net force. He's applying a greater force than the force it's opposing. So it's kind of moving really, really slowly. So friction seems to apply whether something is trying to move or whether it's actually moving. So, in the end, what is friction? Friction is often described as a force which opposes motion or intended motion between surfaces in contact. Now, that surfaces in contact is important. You need two things that actually physically touch each other, and it's either moving or trying to move, and that surface is sort of holding on to whatever it is in contact. So you have to have surfaces in contact. Now, there are two types of friction. The first type of friction is called static friction. Now, the word static basically means not moving. So this is a force that opposes intended motion, okay? Sometimes known as starting friction. Now, in our example of our person that was trying to move our crate, we'll notice that static friction can change. In other words, here we're pushing with 20 newtons and it's not yet moving. So that means static friction exists, and it's equal to 20 newtons at this particular moment. But we saw as we increased our pushing force to 100, it still didn't move, and that static friction force also grew to 100. Now when we hit 125 newtons, found out we were right on the edge of being able to move it. So that means static friction reaches a very maximum amount. Okay, and that maximum static friction is a set value. Okay, now once you get beyond that static friction, things will start moving. So static friction can grow and grow and grow until you reach its maximum point. The second type of friction is called kinetic friction. This occurs once an object is actually in motion. Okay, so kinetic friction occurs after an object has actually overcome static friction and is now in motion. Okay. Now, kinetic friction is also a set value, And it differs in a little way from static friction. As you saw, static friction can grow and grow and grow until it reaches a maximum amount. Turns out kinetic friction, though, is always one set value, one amount, and that amount remains constant no matter how hard you're pushing. One of the most important concepts, your static friction value, your maximum static friction value, will always be larger than your kinetic friction. It always takes more force to overcome static friction to start something moving than it does to keep something moving, in other words, to overcome kinetic friction. So, what dictates exactly static friction versus kinetic friction? Or really, how much friction there really is? Well, it turns out there are two very important things. Now, one of them should be kind of obvious. Now think about it. It's easy to walk on the ground, but difficult to walk on ice. So the difference is the surfaces, ice versus the regular ground. So clearly one of the most important things that affects the amount of friction that occurs is what materials we have in contact. Now, a little about some symbols here. Notice we're using a little lowercase f for friction. That's sort of to distinguish it from any other force. Materials in contact has its own symbol, and that's the Greek letter mu. And this stands for the coefficient of friction. Turns out you can look up all these different combinations. For example, the rubber of your soles of your feet and the ground, and that will give you a certain coefficient of friction. You could also look at the rubber from the soles of your shoes to ice, and that would give you a different coefficient of friction. And because of that, because static friction and kinetic friction are different values, each one has its own coefficient. So again, if you looked up the rubber from the soles of your shoes and ice, you would see a static coefficient and a kinetic coefficient, okay, because these values differ depending on whether you're trying to get something moving or you're actually in motion. So the materials is the obvious part. The second one is not always as obvious. Well, as you probably have experienced, if you try to push something, it's a lot harder to get something moving that's heavier than something that is lighter. So my automatic thought is, well, it's got to be mass. Well, not entirely true. See, for example, it's actually easier to move something down a ramp than it is to move it across the floor. Okay? Even though the object you're moving has the exact same mass. So what turns out, because friction involves surfaces in contact, now remember, what does that force do to surfaces in contact? We call that the normal force. So the other thing that is very important to the amount of friction that you're going to have is the value of the normal force. Not the mass itself, but the normal force. So these two things sort of go hand in hand. So now the normal force becomes a very important thing. We haven't really used it that much before, but now it's very important. So what does that lead to? Well, friction has its own very specific equation, and it looks like this. Friction is the product of mu, the coefficient of friction, and the normal force. Now notice, it's the same equation whether you're talking about static or kinetic. The only thing that's going to be different is that coefficient value. The normal force should be the same in both cases. So let's look at an example. So here, for example, let's say I've got a wooden crate sitting on a stone floor. And I look up in this little table and I find out that for this particular wood and this particular stone, they have a static coefficient of 0.5 and a kinetic coefficient of 0.4. Notice that the kinetic coefficient is less than static, and that'll always be true. Now, let's say I want to move this. My first question is, well, how much force do I need to apply to start it moving? Well, what might help me here? How about a free body diagram? So let's do that. So, my first force that I always like to draw, of course, is the weight. mg, x straight down. Now, the crate is sitting on the ground, so that must mean there's a normal force pointing straight up. Now, you also have the force that someone is pushing with. Okay, so in other words, that's the force we're kind of looking for. What's my pushing force? Where before we kind of ignored friction, now it's coming in. Friction must always oppose motion or intended motion. So since our person tends to push to the right, our friction must act pointing to the left. Okay, so I've drawn my free body diagrams. Next step, let's sum some forces. Using kind of standard axes here. Now, in the x direction, I have two forces. Pushing force in the positive direction, friction in the negative direction, and the sum of my forces has to equal ma. In the y direction, well, I've got my normal force pushing up, my weight in the negative direction down, but those equal 0, okay, because we're not trying to move it that way. There would be no acceleration in that direction. Now, this, of course, is my really important equation. Pushing force minus the friction equals ma. My first question asks, how much force do I need to get it to start moving? If that is starting motion, then I clearly need to know what my maximum static friction number is. Again, I can push with any force I want, but it's really the maximum static friction that becomes important. That's the value I need to know. So let's figure that out off on the side. Static friction is the static coefficient times the normal force. Oh, now look, this normal force equation, that becomes important. Well, that says that normal minus mg equals 0. Well, a little algebra tells me then that the normal force and mg must be the same value. And since I know what mg is, mass is 100, gravity is 10, the normal force is 1,000 newtons. So wherever I see normal force, I can put in 1,000 newtons. So in this case, my static friction must be my static coefficient, 0.5, times the normal force of 1,000, or there must be 500 newtons of static friction. And that's the maximum static friction. That's important. It's the maximum static friction, the amount I need to overcome. So if that's true, then whatever pushing force I need has to overcome 500 newtons of static friction. The mass is 100. Oh, acceleration. Well, I'm not moving yet. So I'm just trying to get it started so it has yet to accelerate. So what that tells me is that my pushing force equals 500 newtons. Now, what that means is that I need to overcome 500 newtons of static friction. Kind of makes sense, doesn't it? Now really, at 500, I'm kind of on the edge of just getting it moving, so really I need kind of 500.0001. But 500 is a good enough answer. Let's look at the second question. Second question says, well, how much force do I need to apply to keep it moving at, ooh, there's an important set of words, a constant velocity? Well, this is interesting, because how do I keep something moving at a constant velocity? Well, here's the interesting thing. Even though he's in motion, my free body diagram doesn't change. There's still weight, normal, we're still pushing, and friction is still resisting us now. So if the free body diagram doesn't change, then these equations don't change either. So in other words, I have the same equation, except now instead of static friction, I have kinetic friction, because it's now in motion. So that means I need to know that kinetic friction number. Well, kinetic friction would be the kinetic coefficient times the normal. The kinetic coefficient of friction is 0.4. The normal force is still 1,000, which means there is 400 newtons of kinetic friction. Now here's something important. No matter how hard I push, there's only 400 newtons of kinetic friction. That doesn't change. I now go back to my important equation. Pushing force minus now kinetic friction equals ma. Well, I need to know how hard I can push. I found out that the amount of kinetic friction is 400 newtons. Mass is 100. Oh, A. Remember we said constant velocity? Well, now we all know constant velocity means a zero acceleration, which means my pushing force must be 400 newtons. Now wait, I know what some of you are thinking. How can I push with 400 newtons, and friction is also 400 newtons, and this thing move? Good question, and probably one of the most confusing things about friction itself. How can I push with a force of 400, friction resists with 400, but it continues to move? Here's an example of just that. Notice that our person is pushing with 250 newtons, and there's a kinetic friction force acting also of 250 newtons. Look up here at the speed. Notice how the speed doesn't change? It's because he's moving at a constant velocity. Whenever forces are in balance, but the object already is in motion, you'll maintain a constant velocity. And that's really the trick. He had to have already gotten it in motion. Now, once it's in motion, as long as you push with the same amount as kinetic friction, you'll move at a constant velocity. And that sort of makes sense. Because, for example, if I were to increase his force, notice that the speed starts to go up because he's got a greater force. If I decrease his force, notice his speed starts to slow down. In other words, I have accelerations when the forces are unbalanced, when I have a net force. But as long as I don't have a net force, as long as the sum of my forces is zero, my velocity is constant. So it is possible to push with the same force that friction's acting and maintain a constant velocity, but you already have to be in motion, and that's the key. You already have to be in motion. If I wanted to create a graph of what this looked like, someone was pushing on a crate that it was not yet moving and was pushing harder and harder until we overcame static friction and then continued to push it so it moved at a constant velocity. What would that graph look like? Well, I'm going to do it on a force versus time graph. Now, if we looked at that example before, remember there were two important numbers. There was the 500 newtons, which was the maximum static friction we had to overcome, and there was the 400 newtons, which is the kinetic friction that occurs no matter how hard we're pushing. So if we were to look at this graph, well, we would start with no force, but we would continue to push harder and harder and harder and harder until we hit that 500 newton part. Now, as soon as we overcome that static friction, kinetic engages, so it immediately drops down to 400 newtons. And now if I want to push at a constant velocity, I just have to maintain that constant force of 400 newtons. So at this moment right here, that's where we overcome our static friction. And this line down here shows we are pushing with a force equal to that of the kinetic friction. And that's basically what the graph would look like. So with that in mind, let's look at another example. Let's say that we got our crate again, and that we're already in motion. Okay, so he's already got it moving. He's overcome the static friction. Okay? And what I want to know is, well, how much kinetic friction is acting here? Well, we kind of already figured that one out. Now notice right now, I don't even need a free body diagram because kinetic friction is solely based on the coefficient in the normal force. It has nothing to do with the amount at which someone pushes. So we've got a kinetic coefficient of 0.4. The normal force, well, we'd figured that out before, was same as the weight, mass times gravity. And so we still have 400 newtons of kinetic friction. Now, here's the question. If our person has the ability to push with 500 newtons of force, what would the acceleration be? Well, again, if we had looked at our free body diagram like before, we have weight, we have the normal force, we have our pushing force, and this time we definitely have kinetic friction. When we sum those forces, we had our pushing force minus kinetic friction equals ma. Now in this case I've told you what the pushing force is. It's 500. We know there's 400 newtons of kinetic friction resisting on a 100 kilogram mass, which leaves an acceleration. Well, it's 100 on this side, 100 on this side, divide both sides by 100, and we get an acceleration of positive 1 meter per second squared. Now, is that a constant velocity? No, it isn't. It means it's going to gain 1 meter per second every second. In other words, it's going to get faster and faster and faster, but just at a really low rate. As long as the forces are unbalanced, you'll have an acceleration. Okay? But again, he's pushing with 500, so we get a positive acceleration. Now, if instead he was to push with a force once it was in motion of only 200 newtons, well, then we'd have 200 minus 400 in kinetic. So this would be negative 200. In other words, we'd have an acceleration of negative 2, which means the thing would start slowing down. And it would keep slowing down and keep slowing down until it eventually comes to a stop. Now, the moment it comes to a stop, static friction re-engages. And now you have to push much harder in order to overcome that. So, for example, if our person here drops his pushing force down to, say, 100, well, now there's a negative acceleration. See, the speed is decreasing. And slows and slows and stops, and oh, notice that the friction dropped to 100 because now we're in static mode. And since we can't overcome the static friction at this point, however hard we push, the static friction matches it until we were able to reach that maximum number. Okay, so that's a good introduction to the idea of friction. Again, to sum up, friction is a force that opposes motion or intended motion between surfaces in contact. The amount of friction is based on the materials and the normal force. When something is not in motion, as you push against it, static friction keeps it from moving. But static friction will grow as you push harder until you reach a maximum value. So static friction can change up until a maximum value. However, once you get something in motion, kinetic friction is only a singular value. It's only set at a maximum value. And remember, whatever the maximum static friction value is, that will always be greater than whatever your kinetic friction value is. All right, I'll see you next time.